All right, this lab is extremely quick and fast to inoculate. If you've looked at it already, you'll know there's only 2 tubes to inoculate. The one test is pretty straightforward, and the other one we're going to have to take a little bit more time to understand really what's going on there. But these are both enzyme tests. So remember your terminology. Enzymes work on substrates, and what you get is some product that's different than the substrate. So if we want to see if our organism produces a particular enzyme, usually the easiest way to do that is to test and see if some product shows up. But sometimes, as we'll find, it works even better to see if the substrate disappears. Because if the substrate's not there anymore, then the enzyme must have been there. So 2 ways to test to see if enzymes are produced by an organism. So our first enzyme test here is phenylalanine deaminase. Okay, hopefully you recognize phenylalanine as being one of our amino acids. So if I drew a structure of just any amino acid, here's the side chain. I'm not going to bother to write down phenylalanine specifically, but if we have any amino acid, and if you have an enzyme that cleaves off the amino group, okay, that's what a deaminase is. It's an enzyme that cleaves off any compound, could be an amino acid, something else, with an amino group. Okay. So our enzyme, phenylalanine deaminase, is one that changes that amino acid phenylalanine into the substrate phenylpyruvic acid. Oops. And ammonia. Okay, so that ammonia comes from that amino group over here. Okay, anytime you see ammonia, you think, probably going to be some alkaline end products there, although we have an acid here as well. So to inoculate, the phenylalanine deaminase tubes are just a slant that's been enriched with phenylalanine. So remember, when you inoculate the slant, you're just going to loop your cells on the surface of the slant. We're going to incubate it, and when you come in next time, we're going to add 5 drops of the reagent ferric chloride. Whoops. And you don't have to do that aseptically. When you come in, you can go ahead and add those drops right in the top. That ferric chloride is kind of yellow. Unfortunately, my picture got turned on its side. I'm not sure why it did that. But for a negative result here, you can just see that yellow ferric chloride. For a positive phenylalanine deaminase test, you see kind of a greenish, kind of a pine green color change on the slant here and anywhere that there's growth. Okay, phenylpyruvic acid is actually a keto acid, and that reacts with the iron there to give a green color change. Okay, so pretty easy. In years past, we've had to kind of look pretty closely at that and kind of turn the tube sideways or whatever to see it a little bit better, but you should have an unmistakable greenish tinge to it there for a positive result if your organism is able to produce that enzyme. Incidentally, as humans, we need to be able to break down phenylalanine as well. We do that with a different enzyme. We have the enzyme phenylalanine hydroxylase, and we get a little different end product. It's one of our other amino acids, tyrosine. If we as humans can't make this enzyme, what disease is it called that we have? And I'll give you a hint, babies are tested for this almost as soon as they're born. It's called phenylketonuria, PKU, if humans are deficient in this enzyme that breaks down phenylalanine. Okay, so essentially people that have this have to be fed a special diet without phenylalanine in it. And it's great that we can catch this now. That's why babies are tested as soon as they're born routinely, because if we don't catch this, then phenylalanine builds up in the bloodstream, and by the first year of life typically starts to cause brain damage. So it's a hassle. There's a lot of therapies kind of coming in now to hopefully make life a little bit easier for people with PKU. But that's sort of just FYI there. All right, the other test that you're going to inoculate is to test for the enzyme nitrate reductase. And again, it's just one tube here, really easy on your lab day to inoculate it. Let's talk a little bit about the significance of this enzyme. Organisms that are positive for this enzyme are able to use nitrate as a final electron acceptor instead of oxygen. Okay, so the so what of that is that allows organisms to respire anaerobically. Okay, and a lot of times students, I think, get confused about what anaerobic respiration is compared to aerobic respiration compared to fermentation. So I just want to give you a 2-minute overview of metabolism to try to parse those terms out in a kind of simplistic way. Okay, so most of the time organisms are going to utilize glucose as their first choice for energy, and of course during glycolysis that glucose gets changed into 2,3 carbon pyruvates. Okay. If a suitable electron acceptor is present, maybe it's oxygen, maybe it's something else, then the pyruvate, of course, gets changed into acetyl-CoA, 2 carbons there, and enters the Krebs cycle, or citric acid cycle, or TCA cycle, whatever you want to call it. And lots of electrons get pulled off of here. We get some in glycolysis as well, but Krebs cycle, again, lots of electrons. That's mostly what it's good at. A little ATP, but lots of electrons. Now, those electrons get dropped off at the electron transport chain. Okay, which remember in prokaryotes is going to be in the cell membrane. Okay, so those electrons, remember we don't write the electron in here, but if the NADs are actually carrying 1 proton and 2 electrons, those electron carriers, and those again then cycle back to their oxidized state. Okay, and in that electron chain, which we kind of usually draw like this, there's some suitable electron acceptor like oxygen. Okay, so that's aerobic respiration. If an organism, if there's no oxygen present and the organism is able to use something else, like say nitrate or sulfate or carbonate as a final electron acceptor, then it will do pretty much the same thing. The Krebs cycle is a little bit different, but pretty much go through the same cycle, only it's nitrate instead of oxygen that picks up those electrons. Okay, and of course there's lots of ATP coming off here. Okay, so we get a little bit less ATP if you use something other than oxygen, some inorganic ion like nitrate or sulfate, but still a good amount of ATP most of the time, depending on what it is. Now, if there's no suitable electron acceptor available, then the cell doesn't have any choice but to use some kind of organic electron acceptor, something in the cell already, typically, because it has to have some way to recycle the NADs just to keep glycolysis moving. Okay, so these NADHs basically get passed back to pyruvate, and then usually we get some kind of acidic end product. It could be lactic acid, for instance, and that's a process called fermentation. Okay, so again, I'm going to talk a little bit more about that next lab because we're going to be inoculating fermentation tubes, but you can see how this process of fermentation is really way different than anaerobic respiration, where we're using something like this. Okay, so again, fermentation is just recycling these NADHs that we get in glycolysis back to the NAD here so that glycolysis doesn't get stopped up. And at least we get a little ATP from glycolysis. Usually there's not any more ATP from what other fermentation pathway is used, but at least we still get ATP from glycolysis. All right, so that's just kind of hopefully maybe help you to make some connections that you didn't have before. Okay, this organisms that are able to make nitrate reductase, I just wanted to show you this here. This is, more complex than what we need in lab, but here's the enzyme nitrate reductase. If organisms have this enzyme, that's an enzyme that's right down there embedded in the membrane. You might recognize this cytochrome B as one of the cytochromes in the electron transport chain. So if the organism has nitrate reductase, then that enables the organism, again, to reduce nitrate or to use nitrate as a final electron acceptor. Okay. All right, so what does this enzyme do? Let's write out the reaction here. Okay, so nitrate gets reduced to nitrite. Whoops. Nitrate reductase. Okay. Nitrite. Okay, so that's what the enzyme does. Okay, and you're going to be inoculating a broth. Again, with your loop, it's a broth that's been that has some potassium nitrate in it, the source of nitrate ions. Okay, so you're just going to inoculate that. We're going to incubate it. When you come in, we want to test to see if this product, nitrite, is there. Okay, and we can do that by the addition of two reagents. We're just going to call them reagent A and reagent B. So nitrate reductase reagent A, nitrate reductase reagent B. In your book, it lists what those chemicals really are. Reagent A is NN-dimethyl alpha naphthylamine, and reagent B is sulfonilic acid. Okay, A and B is good enough for me. I think it's 5 drops of each. And if you get a red color change, then that's a positive result. These are testing for the presence, again, of nitrite. So if nitrite is there, then we get a red color change, and that tells us that the organism must be producing the enzyme nitrate reductase. Pretty easy, right? Well, if we get no color change, we have to consider the possibility that the organism may have had this enzyme, and it also had other enzymes that further reduce nitrite down in kind of a stepwise way into nitric oxide, nitrous oxide, or nitrogen gas. Okay, if the enzyme has these enzymes like nitrate reductase, then you're not going to have any of this nitrite left as kind of an intermediate there. You're going to have your end products down here. Okay, and this process of reduction of nitrate all the way down to these gaseous end products is called denitrification. Okay, so if you have a denitrifier, the organism's got the enzyme, but it's not going to test red here. So we have to see if you have no color change, is that because the organism is a denitrifier, or is it because it just doesn't have the enzyme at all? Okay, so if there's no color change, you will have to add a little bit of zinc powder. You can do that by just sticking a wooden stirring rod into the zinc powder, and then whatever sticks to that, you swirl around in your broth. It doesn't take very much. The zinc powder is a reducing agent. Okay, it reduces nitrate to nitrite. Okay, so if now, after you add the zinc, you get a red color change, then that is a negative result, because that means that there was substrate left in the medium that the zinc now reduced to nitrite. And these reagents A and B are now making the nitrite turn red. Okay, so that means it's the zinc that reduced it and not the enzyme, and the organism must not have had the enzyme. If you still get no color change, then you know you have an organism that does possess the enzyme. It's also a denitrifier. You're probably going to see a gas bubble in the Durham tube. And I forgot to explain what that is. Actually, in the tube that you inoculate, there's a little inverted test tube in there. We call that a Durham tube. That tests for the presence of gas. Okay, so if you have a denitrifier, you're probably going to see a little gas bubble in there. You have to look pretty hard, but that gas bubble is maybe nitrogen gas or nitrous oxide or nitric oxide. Okay, so it's a little bit convoluted. Hopefully it will make sense. When you add the reagents, give it a little bit of time. It starts out light and will get darker and darker red. So give it a little time, give it a little finger tap, and see if it's going to turn. Okay, so you'll use the same organism to inoculate both your phenylalanine deaminase slant and your nitrate reductase broth.